Hey, in this video, we're going to take a look at some identities or some consequences that come from what we know about this main six trigonometric functions. Um, so we're going to learn about some new identities and some interesting things that can help us simplify expressions that contain sine, cosine, tangent, and their reciprocal functions. So, for example, if I asked you to simplify the expression tangent theta times cosine theta. On the surface, that doesn't look like there's much I can do. They're not like terms. I can't really multiply them together. But if I think about the fact that tangent is uh, alternatively defined as sine of theta divided by cosine theta, what that will allow me to do is we'll get to see some algebraic simplification that comes from this. So if I rewrite this as sine theta over cosine theta, that's tangent, and I multiply by cosine theta, I could make this a fraction if I wanted to, over 1. What will end up happening is when I multiply across the top and the bottom, I'm going to have sine theta, cosine theta, divided by cosine theta times 1. And then those cosines can actually divide and make 1 or cancel out because I'm using multiplication throughout this entire fraction. So that cosine will cancel or make 1 when divided by the other cosine. And so this expression can simply be written as just sine of theta. And so this is what we're going to start to look at today is like, how can I manipulate expressions that don't look like they can be simplified, but they actually can? And if I look at something like secant theta and cotangent theta, I know secant, an alternate definition of secant is 1 divided by cosine. Tangent is sine over cosine, so that means cotangent must be cosine over sine. And again, I see that I have a common factor of cosine in the denominator and the numerator. This time I'm not going to multiply them together because I'm just going to cancel those out anyway eventually. And so what I'll have is 1 divided by sine of theta. And that is simplified. We should, if the entire answer can be written as just a single function, I want to do that. So I'm actually not going to leave it 1 over sine theta. I'm going to write this as cosecant theta because that is, right, cosecant is defined as 1 divided by sine. So they're my two expressions, or the simplified version of those two expressions. And these are the sorts of things that we're going to work with in this video. Again, just a real quick reminder, those are the reciprocal. Every trig identity or every trig function can be written as the reciprocal of another trig function. But we are going to try to work everything back in terms of sine and cosine as much as we can. The quotient identities, again, we just use both of these. Tangent is sine over cosine. Cotangent is cosine over sine. And that's going to help us out in just a few minutes. The Pythagorean identities are different ways that we can create one in the scope of working with triangles within the unit circle. If you remember the fact that we talked about the sine of an angle corresponds to the y coordinate on the unit circle. Sine squared is essentially y squared plus cosine squared is x squared. And that comes from the fact that if I were to draw a right triangle like I would have on the unit circle, if I go 30 degrees here, this is y, this is x, and we know on the unit circle that's 1. So what I essentially have is the Pythagorean theorem within the unit circle. So sine squared plus cosine squared will always equal 1 because on the unit circle, those each correspond to a leg of the right triangle. And then you can do some, I'm not going to prove the other two, you can do some manipulation of this first identity, sine squared plus cosine squared equals 1. And you can come up with these other two expressions as well. These other two identities. Tan squared plus 1 is equal to secant squared, and 1 plus cotangent squared is equal to cosecant squared. We're mainly going to use the top one, but the other two will be used from time to time. Even and odd identities, how this works, an even function is a function or a function in which you could make the input negative, but still get the same output. So for example, if I asked you, what is the cosine of negative 45 degrees? That is, if I were to make the unit circle, the cosine at negative 45 is root 2 over 2. But that's also the same as cosine of positive 45. And this is true. So for cosine, I could pick any angle, and this relationship would be true. Cosine of negative 60 is the same as cosine of positive 60. So with cosine and secant, because secant is the reciprocal of cosine, if I make the input negative, that actually doesn't change the output at all. So effectively what I can do is if I see cosine of negative x, that is just the same as cosine of x. Okay, so cosine and secant are what we call even functions. That negative in the input can be removed and without changing the value. Odd functions are kind of the opposite. An odd function, if I make the input negative, it will make the output negative. Meaning, for example, if I asked you what is the sine of negative 45 degrees, that is negative root 2 over 2. Compared to the sine of positive 45 degrees, that is positive root 2 over 2. So by making the input negative, all I'm doing is I'm keeping the same value, but I'm making the output negative. And that is something that is true for any angle I plug in. Sine of negative 90 is just the negative version of sine of positive 90. And so the other four trig functions are what we call odd functions. So sine, cosecant, tangent, and cotangent are all odd functions. The cofunction identities are essentially just saying if you subtract, like I can relate sine to cosine really well. The sine of 30 degrees is the same as the cosine of 60 degrees. And there's a relationship there that it's not a coincidence that the sum of 30 and 60 is 90 degrees, or in radians, pi over 2. And so what ends up happening here is if I wanted to say, what's the cosine of pi over 8? That is the same as the sine of pi over 2 minus pi over 8, which on the surface isn't super helpful for us. But as we'll see when we start trying to simplify expressions, these cofunction identities will allow us to change a cosine into a sine or vice versa. So once you're back in class, what will happen is I will give you a trig formula sheet that looks like this with all of these different identities on it and formulas. It looks really overwhelming, but basically what we just covered is the top half of that sheet. The reciprocal, the cofunction, all that good stuff. So here's a slightly zoomed in version of those identities. Again, just kind of a quick little summary of those. And so now what we're going to do is we're going to apply those to simplify things like we did in the warm-up. Really, like, not every single one of these has to be memorized, but you should have some of the big ones like sine squared plus cosine squared equals 1. It's going to be easier if you know the trig identities. So for instance, if I asked you to simplify this expression, cosine of pi over 2 minus x over cosine of negative x. Well, we talked about the denominator already. The cosine of negative x is the same as cosine of just positive x, because cosine is what's called an even function. And then cosine of pi over 2 minus x, if I scroll back up here, I can see cosine of pi over 2. They use u, but the variable can be swapped out. The cosine of pi over 2 minus u is just equal to the sine of u. So if I replace the u's with x's, what that tells me is that this is the same as just the sine of x. So this whole expression, or that whole function right there, can be written as the sine of x. And now I have sine of x divided by cosine x, which can be simplified into just tangent. So that function in the beginning that expression that looked really wonky is actually just equal to tangent of x. So these are, again, the kinds of things that we're going to, hey, here's this crazy expression. Can you simplify it down? Okay. Not much I could do at the bottom, right? Secant x, I could call it 1 over cosine, but I'm going to wait on that because I got to clean up whatever the heck's going on in the top of this fraction. I have sine squared plus tangent squared plus cosine squared, but because everything's added together, addition is commutative. I can reverse the order, and that's not going to matter. So what I'm going to do is I'm going to choose to write this as sine squared plus cosine squared plus tangent squared. And the reason I'm going to do that is because I know something about this. I know sine squared plus cosine squared is just equal to 1. So what happens now is this expression becomes 1 plus tangent squared over secant. Okay, bless you. And now the numerator is 1 plus tangent squared, which feels like it's not super helpful. But if we look, our second Pythagorean identity is 1 plus tangent squared is actually the same as secant squared. So that means I can come back down here and I can call this secant squared over secant. And secant squared just means it's secant multiplied by secant. So what ends up happening here is I can cancel that secant in the denominator with one of the secants, or one of the powers of secant, in the top. And so what I end up with is simply the secant of x. So this big crazy long expression, sine squared plus cosine squared plus tangent squared over secant, actually was able to be consolidated all the way down to just secant. Again, there will be times where this is frustrating because you don't really know where to go. If you're not sure, turn everything into sines and cosines and then just start, as long as it's legal algebra, we can start just manipulating and putting things together and see where it goes. And so we're going to do that here. I'm not going to use that formula sheet. I'm just going to take everything and I'm just going to brain power this into sines and cosines. Cotangent, well, that's cosine over sine. Secant is 1 over cosine. And then on the denominator, I have cosecant, which is 1 over sine. Okay. Now, if I draw my attention just to the top of this fraction, if I ignore the 1 over sine x on bottom, I see that here I have a cosine x and a cosine x. I have that common factor cosine on top and bottom. So what happens here is I can turn this into, the top can be written as 1 over sine x, and then the bottom is 1 over sine x. Now, I could just cancel those out and call it 1, but you will have to take a fraction and flip and multiply from time to time. So what I'm going to do is I'm going to take this and I'm just going to rewrite it as, we know that if we're trying to divide fractions, I can instead multiply by the reciprocal of the bottom fraction. So I've got sine x over 1. Those common factors of sine can be canceled out. And then I can just write this expression as 1. So that expression, cotangent times secant divided by cosecant, can be simplified all the way down to just 1. Again, we didn't use the formula sheet. We just put everything in terms of sine and cosine. So the third and final tip I'm going to tell you is, if you're not sure what to do, try to find a common denominator, because that will allow you to combine multiple fractions. And that will help us when we need to simplify things. So let's try that out here. I have the expression cosine plus tangent times sine. So cosine, can't write that any other way besides maybe cosine over 1. Tangent is sine over cosine. Sine is sine over 1. And so now what I have, if I multiply the two fractions together, I've got cosine of t over 1 plus sine squared of t over cosine. So I've combined those two fractions. I want to add them together, but in order to add fractions, I do need a common denominator. A denominator of 1 is really nice algebraically to deal with because I can turn 1 into anything. So what I'm going to do is I'm going to multiply the top and bottom of this expression by cosine. I'm going to multiply by cosine. And so what that will give me now is that first fraction can be written as cosine squared over cosine. And then my second fraction is sine squared over cosine. Cosine squared plus sine squared. We already know that that is equal to 1. I'm going to write it out once, or write it out with the consolidated fraction, just to really reiterate the fact that when we add those fractions, the denominator is common, but it stays the same. So then from here, I know cosine squared plus sine squared is equal to 1. So this becomes 1 divided by the cosine. And that, of course, can be written as the secant of t. So in this example, we were able to simplify the expression all the way down to just the secant of our variable t. So if you're trying to add two fractions or two functions, oftentimes if you write it as a fraction and then get a common denominator, that will allow you to combine and oftentimes be able to consolidate or cancel something out. I believe this is the last one. So let's take a look at, if I just give you these two fractions, I can't rewrite these in any way. I can't 1 minus sine x as a denominator. I can't write this as cosecant at all. So what I need to do is I need to go right into getting a common denominator. Now, I can only use multiplication when I'm manipulating or changing a fraction. So I can't just like add, two sine of x to the first fraction so that the common denominator is there. What I need to do is I need to take each one of these and multiply the second fraction by the denominator of the first, and multiply the first fraction by the denominator of the second. So what I mean by that is I'm going to go ahead and write as 1 minus sine x on top and bottom. And then the first fraction I'm going to multiply by 1 plus sine x on top and bottom. Sorry about the border of the page there. And what that's going to do for me is I now have 1 plus sine x is my numerator of the first fraction. And then my denominator is actually going to be, let's try and keep this coordinated. It's going to be 1 plus sine x times 1 minus sine x. 1 minus sine x. And then I'm going to add that to my second fraction, which is 1 minus sine x over 1 plus sine x and 1 minus sine x. So now what we can do is we can add those numerators together. And when I do that, the sine x's are going to cancel out and just give me 2. So I'm going to have 2 over that big common denominator. And if you remember, when we multiply two expressions, like if we FOIL or distribute or whatever, and they are one's 1 plus a function and the other one's 1 minus, there's actually going to be some really convenient cancellation here. So I'm going to go ahead and multiply these together. And if I think about what happens when I distribute or FOIL, whatever you want to call it, let's go, I'm not going to draw the arrows, but if I take this thing right here, I'm going to have 1. My second term is going to be minus sine x. My third term is going to be plus sine x. And my fourth and final term will be negative sine squared of x. The sine x's in the middle will cancel, and so then this can become 1 minus sine squared of x. Okay, so that's actually my new denominator, 1 minus sine squared of x. You might be thinking, what the heck? Why is that even remotely helpful? It's nice that the numerator is just 2, but why would we write the denominator as 1 minus sine squared? And the reason that we're going to do this, and I'm going to go back to a previous page here real quick and show that these identities that we've learned can be used in more than one way. Meaning, sine squared plus cosine squared equals 1. I could take this expression and simply subtract sine squared from both sides. And now I have a new identity, which is that the cosine squared is equal to 1 minus sine squared. Clearly, 1 minus sine squared is what my denominator was. So that means the denominator of the problem that we're working on, which I'll go back to in here in just a second, can be rewritten as simply cosine squared. So I'm going to get rid of this, and we're going to go down, and we're going to see that this denominator can actually just be written as cosine squared. Oops, that was too early. Right here. So this expression can be rewritten as 2 divided by cosine squared, which is really just 2 divided by cosine times cosine. But the reciprocal of cosine is secant. So what I can do with this is I can think of it as 2 times 1 over cosine and then squared. That's another way that I could like break that down just to really see that I do have secant in this problem. So my ultimate simplification of this is going to be secant squared of x multiplied by 2. So all of that, and we were able to simplify the expression down to just 2 times secant squared of x. This is not an exhaustive list. This is not all the different things you'll be asked to do, but this is just showing you some of the different ways that we can use these trigonometric function identities. Okay, so again, know your trig identities. If you're not sure, turn everything into sine and cosine. And then if you need to, if you're dealing with fractions, go ahead and get a common denominator so that we can simplify them. And that is going to end this video.